Chapter number 3, digital signals and systems. So starting this chapter, we are going to look at how to define digital signals and how to analyze digital systems. Digital signals, we have discussed so far digital signals. We have sampling, we have quantization, and finally we have the digitization, that is a sample value converted into combinations of ones and zeros. In general, when we talk about digital signals, basically we are talking about that you take the sample of a value, you quantize that value, so it becomes discrete time value, it exists at only one time instance, and we take that value as a digital signal. So before even we convert into digital signal, we assume that this discrete value is our digital value. And many times, all you have to do is to take the sample and treat that discrete value as a digital value. So whichever way we are doing, but the main idea of digital signal that is used in majority of the DSP application is the value that you are taking. Let me go ahead and grab pencil. So when you have x of t, let's say you have x of t 2t cosine 5000t. Let's say you have the analog signal, and if your sampling time is 4 millisecond, whatever, right? Then you take the samples x of nts is equal to 2 times nts cosine 5000 times nts, where n basically starts at 0. So in digital signals, your first sample is the 0th sample. So if I ask you calculate the 10th sample, n will be 10 for that, right? N will be 10 for that, but the sample number will be starting at 0. So 0, 1, 2, 3, 4, all the way up to 10. Total number of sample when you get to 10 are going to be 11 samples, but again the count starts at n is equal to 0. So if I say calculate 10, that means n is equal to 10, as simple as that. Okay, so these values in general we drop ts, because ts is a common factor, right? ts is not changing, only n is changing over here. So 0, 1, 2, 3, each multiplied by ts, of course, to calculate the sample value, but ts is not changing. So to represent the digital sequence, all we represent is x of n is equal to, let's say, 1, 3.3, 5.7, 6.8, and whatever. So this is considered as a digital sequence, and these numbers are usually quantized values. But even if you're not doing the quantized value, you're just calculating the samples and making a sequence out of it at discrete time, and that time, of course, is the quantized time, sorry, not quantized, sampling time. The signal is going to be considered as a digital signal for the processing purpose, for the analysis purpose. Okay, of course the real digital signal, remember, is going to be what? Coded in binary. But for the analysis purpose, this will be considered as digital signal, and we drop ts. As I said, ts is a common factor, but to get the signal values, of course ts has to be there, remember that, because you are sampling it. So this is what I'm discussing over here. Digital signal is shown over here. X of n, x of 0 is 2.25, x of 1 is 2, x of 2 is 1, x of 3 is -1, and then 4 and all other values are 0. So we have some important digital signals that we use, and the first important digital signal is the step or unit step signal. What is a unit step signal? I'm pretty sure most of you are familiar with the unit step function. A unit step signal is basically a signal which will have a value of 1 for all of its argument, 0 and positive. What is the argument? Basically, argument is whatever written in the parentheses. So this is called argument of the function, right? So as long as this argument is 0 or positive, the value of the step function will be 1. If this argument becomes negative, then for all those values for which the argument is negative, a step function is going to be 0. So that's how you define the step function. So for example, look at this. If you have un minus 4, when the argument will be 0, for which values? For all the values of n greater or equal to 4, the argument will be 0 or positive. So un minus 4 will be 1 for n greater or equal to 4, and for all the values less than 4 and negative, including 0, it is going to be 0. Un plus 10 is going to be 1 when n is greater or equal to negative 10. So negative 10, negative 9, negative 8, 0, positive values. For all those values, a step function is going to be 1. And for values less than negative 10, negative 11, negative 12, it is going to be 0. If you multiply any signal by unit step, basically, unit step has a magnitude of 1. So any signal that is multiplied by unit step is going to be the value of that signal. But it's going to start, the signal is going to start when the unit step function is going to start, right? That is when the argument of unit step is going to become 0 or positive. So many times, if you want to show that a function is starting at 0, many times we just write down x of n, u of n. And this shows that function is going to start at 0 because u of n is going to be 1 at 0 and all the positive values. But for values n less than 0, this function value is going to be 0. So it will not have any value for less than n. Okay, so these are some unit step sequences based on when the argument becomes 0 or positive. The second function, important function, is unit impulse function. An impulse function basically has the value of 1 when its argument is 0. And for any other value of the argument, the impulse function is going to be 0. So impulse function delta n is 1 when n is equal to 0. Delta n plus 10 is going to be 1 for n is equal to negative 10, where the value of the argument becomes 0. And for all the other values is going to be 0. So impulse function produces one value only on the scale of n. So look at the example. Xn is equal to 2 cosine 2333 n delta n minus n naught. When the value of this function is going to exist, when the impulse value is going to be 1, which will be at n naught. So basically the value of this function is going to exist only at n naught, and rest of the values will be 0 because you are multiplying the function by impulse function, and impulse function will be 0 at other values except at n is equal to n naught. So there are some examples that are given here. I'm asking you to plot a digital signal which is given by 5un plus 3 minus 2un and 3 minus 3un minus 4. So 5un plus 3, it is going to start at n is equal to negative 3, right? And the value of the signal is going to be 5. So it's going to start 1, 2, let's say this is n is equal to negative 3. Now this signal is going to start at n is equal to 0 and the value is going to be negative 2. So I have negative 3, negative 2, negative 1, 0, 1, and this function will keep on going, of course. Just this function I'm talking about. But at n is equal to 0, the other function is going to start as well, negative 2, right? So n is equal to 0, which is here 1, 2, 3, 4, negative 3, negative 2, negative 1, 0. So at n is equal to 0, the negative 2 function is going to start as well. And it will keep on going, remember. Only this part of the function, I'm drawing here. So this is negative 2 value, and this is 5 value. And then so before we discuss the last part of the function, so at n is equal to 0, before n is equal to 0, the value of the function was 5. But at n is equal to 0, you have 5 and then you have -2, and you are adding them together, right? So the total value of these two is going to become 3. So at n is equal to 0, the function value is going to become 3 instead of 5. So this is 5, and at n is equal to 0 is going to become 3. 5 minus 2. And then at n is equal to 4, you subtract 3 from the function as well, because this part of the function is going to start, and the value of this part is -3, and that will start at n is equal to 4, and it will keep on going after n is equal to 4. So when it will reach to 4, so now you have 0, 1, 2, 3, and then when it will reach to 4, you have 3 going on already, and then -3 is going to be subtracted from there, so the value of the function, total function, is going to become 0. So if you want to plot this signal, this is how the plot is going to look like, and this is the explanation that I just gave you, and the explanation is written as well, of course. Example 3.2, you have one signal which is impulse, which will only exist at n is equal to -5 right here, and then rest of the two parts of the signals are unit step, and they're going to work similarly as we discussed in the last example. Example number 3, a time dependent signal xt is this, sampled with 333 microsecond. Plot the first 10 samples of the signal. So it's just the plotting of a digital signal. Xn is equal to xnts, and you take n, right? First 10 samples means you're going from 0 to 9. N will start from 0, it will go up to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 to 9 right here. And you can plot those samples, you can calculate those samples and plot those samples.